In this video, we're going to look at the measures of the spread of data. So we're going to talk about variation. We're going to talk about range and variance and standard deviation. So what is standard deviation? Well, a couple of things. It is at least 0 or larger, so it's always a positive number. It's a numerical measure of the overall amount of variation in the data. And we use it to determine the particular data value if it's closer to or further from the mean. We call that the z-score, which we'll talk about at the end of this video. The standard deviation, when the standard deviation is small, then the data is pretty concentrated close to the mean, exhibiting very little variation or spread. If the standard deviation is large, then the data values are more spread out from the mean, exhibiting more variation. A data value that is 2 deviations, so we're going to figure out what a standard deviation is, from the average is just on the borderline that many statisticians would consider to be far away from the average, whether it's below or above. Now, if we consider data to be far away from the mean if it's more than 2 standard deviations, we usually call that the rule of thumb, but it's not like the end-all, and it's not a rigid rule. So in general, the shape of the distribution of the data affects how much of the data is further than 2 standard deviations, and we'll learn more about that and the z-scores, and we're really going to use the z-scores later. We're going to explain what a z-score is in this video, and then we're going to use it a lot more later. So this is the first time we're going to talk about a z-score. So what the standard deviation is it really depends on whether or not we're talking about the population standard deviation or the sample standard deviation. Now, in an ideal world, the standard deviation of the sample should reflect the standard deviation of the population. We're going to introduce 2 different symbols. So when we see these symbols moving forward, so make sure as you are writing down somewhere in your notes, these are the symbols I need to know to be successful in this class. Here, S is going to represent the sample standard deviation, and this sigma, this funky looking like O with a line on it, sigma is going to represent the population standard deviation, okay? So sigma for population, S for sample. But before we can even really talk about standard deviation, we need to talk about variance. What is variance? Well, variance is the average of the squares of the deviations. So in other words, X is the data piece and X bar is the average. Now we talked about what X bar was in previous videos. So again, this is something you would have to be able to quickly look at. This symbol in this class with this X with a bar over top, X bar, is the mean, and this mu, this funky looking U shape, is the mean for the population. X bar is the mean for the sample. So what variation is the average of the squares. So what I'll do is I'll take my data piece, I'll subtract off the mean, and then I'm going to square it. So sigma squared represents the population variance, and S squared represents the sample variance. Now, how are these related to standard deviations? Well, variance is sigma squared or S squared. Standard deviation is just sigma or S. So how do we find these? Well, back in the day, we would have had to put all of this stuff in our calculator and do it by hand. Here is the formula for standard deviation for the sample, and here is a formulation for the standard deviation for the population. Notice that with the sample deviation, we have the number of pieces of sample data, so we have like say 26 pieces of data. We do need to subtract 1 for it. And we'll talk about it in greater detail why that's important. And so my sample deviation is going to be the square root of the sums of my frequency multiplied by this difference squared divided by n minus 1. The formula for the population deviation, sigma, is going to be the summation of f of x minus mu squared over n, where n is the size of the population. We almost never will be able to use this one because we almost never have the exact population size. However, sometimes if the population is small enough, we'll be using this. So S is going to mean sample deviation and then sigma is going to be population deviation. make sure you write that down somewhere. So if I were asked to find the mean and standard deviation for on a baseball team, the ages of each of the players were as follow. We need to decide whether or not this is a sample or if this is a population. Well, because we're looking at a single baseball team, this is not going to be all baseball teams. So this is a single baseball team, so this is going to be a sample. So if I want to find the mean and standard deviation, then as before, what I would do is enter all of these either in a spreadsheet or in my calculator and then divide it all by the number of pieces that I have. So I would sum up, so that remember that funky looking thing means sum. This means sum up. I'm going to sum up all these numbers. So I'm going to sum up these numbers, which is 21, 21, 22, 23, and I would sum all those up and then divide by the number of pieces. In this case, I went ahead and I did this on a spreadsheet, and I got the sum, and then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So I have 25 pieces of data divided by the sum, or the sum divided by the number of pieces of data is the mean, and I ended up with 30.68. So that is the mean. Now, the standard deviation, this is going to be S, because this is just a sample. And this is a single baseball team. This is not all of the baseball teams. And I got a standard deviation of 6.094. Now, I could do it by hand by using, let me just scroll up here. I could do this calculation by hand by using this formula, or I can, of course, just put this into a spreadsheet, and there is there's a video in the Canvas shell on which one of those standard deviations to use. If you're using Excel, it would be an equal sign and ST, and then so it starts to pull up standard deviation. You're going to want to use the one that is S, not the mu. Okay, now, since we know the standard deviation S was 6.0945 approximately, and my mean, which was X bar, was equal to 30.68. If I want to know the value that is 2 standard deviations below the mean, I would take the mean value, so 30.68. I'd subtract off 2 times my standard deviation. And my final answer is 18.491. So that would be 2 standard deviations below. If I want 2 standard deviations above, I would do the same thing. I would take my X bar, and then I would add to it 2 times my standard deviation. And then I could tell you what is the one I would expect to be on the upper end of my data. Now, how do we do this if we have a grouped frequency table? Well, when we have a grouped frequency table, what we'll need is we will need to have the midpoint. So, of course, I'm going to add the midpoint just like I did when I was finding the mean for our frequency tables and our grouped frequency tables. So if it's frequency tables, I didn't need the midpoint, but the grouped frequency tables I did. So I'm just going to go 1 and then 4, and then my next number is 7, 10, 13, and 16. Okay. So with this, I'm still going to need to find out how many pieces of data I have, and I added this all up, and I have 26 pieces of data. Now, the first thing I'm going to do is I'm going to find the mean, just like I did before. So to find my mean, I'm going to multiply my frequency and multiply it by my midpoint. And then I'm going to add all of these up. So I'm going to have 1 and 24, 70 and 70 and 0 and 32, and I add all these up and I get 197. So my X bar is going to be 197 divided by the 26 pieces of data. So in this case, my mean was 7.0 577. We'll go to that many decimal places. Now, to do my standard deviation, because I need to have this, which is the sum of my frequency times its midpoint. But when I'm doing a grouped frequency, I need to find my midpoint, and I'm going to subtract off my mean. So I'm going to do that midpoint value, which is 1, or excuse me, my midpoint value, and this is 1. Subtract off this. I'm going to fill in this table. Then the other thing I'm going to need is going to be my m minus x bar, the quantity squared, multiplied by my frequency. That's the thing that I really need. So I would add another one in which I'm multiplying my frequency multiplied by my mean minus my x bar, the quantity squared, where x bar is, it's the midpoint, excuse me, my midpoint minus my x bar, which my x bar is the mean for the data set. Okay, and then I'm going to sum that up, right? So I'm going to sum up that column, and when I did all of that work on my spreadsheet, I got 306.462. Now what I have to do to get the standard deviation is I have to take this number and then divide by my frequency. So my standard deviation, which is S, I got all of this to be, and don't forget it is my mean minus 1, it is going to be the square root of the summation 306.462 divided by 25, and I got the standard deviation to be 3.05-ish. So what I did is I found this f times my midpoint minus my x bar, the quantity squared. This is the n minus 1, where my n was 26, so that's why that's 25. I take the square root of that. If I want the variance, I don't take the square root of it, and then here is my standard deviation. Now, as promised, I said I was going to talk a little bit about z-scores. We're going to really talk about it in a later video, but I want to talk a little bit about the z-scores. And so standard deviation gives us the ability to look at what's happening with different data sets. So we want to look at something called a z-score. And this allows us to look at the means of different data sets, a particular value for different data sets, and then determine which one is the better choice. So we can use these things called z-scores to help us make decisions. So here is the formula for the sample. The piece of data that you're looking at is equal to x bar, which is the mean, plus the z-score times the standard deviation. More often though, we really want to find the z-score. So this is the formula that you would use. So you'd have the z-score is equal to the data piece that you want, minus the x bar mean divided by the sample deviation. And here it is for population. The z-score for population is going to be x minus the mu divided by sigma. So for any data set, at least 75% of the data is within 2 standard deviations of the mean. At least 89% of the data is within 3 standard deviations of the mean, and 95% of the data is within 4.5 standard deviations of the mean. And this guy's rule. Don't ask me to pronounce it because I will butcher it, but that's for any data set. What we're going to spend a lot of time is bell-shaped or symmetric data sets, and this is slightly different. When we are looking at bell-shaped and symmetric, we're at 68% of the data will be within 1 standard deviation, 95% of the data will be within 2 standard deviations, and 99% will be within 3 standard deviations, both below and above from the mean. And this is called the empirical rule. And this only works for the symmetric or bell-shaped. We're going to call this later the normal or Gaussian probability distribution. Now, back to the z-scores. A negative z-score means the data point is below the mean, and a positive z-score means that it's above the mean. We're going to use z-scores to determine, in this case, these two swimmers, Angie and Beth, from two different teams, wanted to find out who had the fastest time for the meter freestyle when compared to the team. Which swimmer had the faster time. Now, Angie, in and of herself, had a shorter time than Beth, but when we compare her values to their team, that may not be true. So we're going to use the z-score to do this comparison. Now, the way that we find the z-score, and these, of course, will be samples, is we're going to take Angie's first, and her score with 26.2, we're going to subtract off the mean, which is 27.2, and then we're going to divide by the standard deviation. When I get done, I get a negative 1.25. So she is faster, by the way, than the team, which we knew by just looking at it. She's more than one standard deviation faster because it is negative and it's below the mean, so it is faster. If it was positive, it would be above the mean. So she seems to be, you know, like faster than Beth. But now let's see what happens with Beth when we compare her to her team. So when we take Beth's score, which is 27.3, and we subtract off the 30.1, we divide by that standard deviation of 1.4, we actually get a negative 0.2. So even though Beth's score is, her time is longer than Angie's score, Beth's score compared to the rest of her team is 2 deviations below the mean. So comparing Beth to the rest of her team, she's much faster than Angie is compared to the rest of her team. Now let's talk a little bit about these standard deviations. Now Angie's team, because it's a 0.8, says that almost everyone on Angie's team is pretty clustered close to the mean team score. With Beth's team, who has a standard deviation of 1.4, that means that Beth's team isn't as close to the mean average time. So Angie's team pretty much all are around that 27.2 mark, whereas Beth's team, they're not as closely clustered as Angie's team. So to answer the question, the answer is Beth, because she's actually 2 deviations below her team average, and when we're comparing it team from the swimmer to their team. If we compare them to each other, obviously Angie is the quicker swimmer.